Let's provide some examples for calculation of line integral of second kind. Example 1. We need to calculate integral by L xy dx plus z dy plus x squared plus y squared dz. L is provided as parametric curve a cosinus t, a sinus t, b t. T belongs to interval 0 pi over 2. Now, what will we get? Here we have to transform this to p of t, r of t, q of t, and differentials have also be transformed. And differentials are also to be transformed. Now, dx will be differential of a cosinus t will be minus a sinus t dt. dy will be a cosinus t dt, and dz will be b dt. Now this integral will be transformed into integral from 0 to pi over 2. xy will give us a square cosinus t sinus t, and dx will minus a sinus t dt plus integral from 0 to pi over 2. Now we have z bt multiplied by dy or a cosinus t dt plus integral from 0 to pi over 2. X squared plus y squared are just a square multiplied by dz, this is b dt. Now we just have to calculate these three integrals. So we get first integral will be ab, integral from 0 to pi over 2, t cosinus t dt. Actually it will be second integral. First integral will be a cube, integral from 0 to pi over 2, cosinus t sinus square t dt, and final integral will be a square b, integral from 0 to pi over 2 dt. Let's calculate these integrals. First integral will give us first integral is integral that has to be calculated by parts. Here we'll get a b t sinus t minus a cube over 3 sinus cube 3 plus a square bt plus ab cosinus t. This will be from 0 to pi over 2, and in the end we will get minus a cube over 3 minus ab plus bab over 2 plus a square b pi over 2. This curve L that we provided in such a way is actually a line that is wrapped around a cylinder. Of radius a. Next example, let us have some line ABC. This line is defined by points A1, 1, B3, 1, C3, 5. And we have to calculate integral by ABC. x cubed plus y dx plus x plus y cubed dy. Here we can split this integral into two because we have line that's not smooth. Actually, we have A, B, C. We will first calculate integral by AB, then integral by BC. A is 1, 1, B is 3, 1, C is 3, 5. Now, integral by AB will provide us with the following. Here, x is changing from 1 to 3. Y is constant. Y equals 1. Then we will get the x part. Integral from 1 to 3. Here x cube remains the same, y is 1 and the x in the end. Plus, here is dy, but y is not changing, so differential of y will be 0. Here we'll get x power 4 over 4 plus x from 1 to 3, and we will get 22. BC, x is 3 but y is changing from 1 to 5. Now we'll get other part working. We'll get integral from 1 to 5. Dx will be 0, so this part will go off. But here we'll get 3 plus y cube dy, which will give us 3y plus y power 4 over 4 from 1 to 5, and which will be 168, and our integral will be totaling 190. 22 plus 168. One more example. When we apply Green's formula, let us have some circle with some radius r. Its equation is x squared plus y squared equals r squared. And we have L as counterclockwise line that surrounds this circle, and D is the region inside circle. And we have to calculate integral by L by closed contour 1 minus x squared y dx plus x 1 plus y squared dy. Here we can use this Green formula. We'll get p dx plus q dy as a double integral by region D, derivative q by x minus derivative p by y, dx dy. Here p is 1 minus x squared y and q is x 1 plus y squared. Okay, derivative p by y is 1 minus x squared, derivative q by x is 1 plus y squared, p derivative, q derivative are continuous inside region D, and this L is smooth curve, so we can apply Green's formula. Let's apply it. We'll get double integral by region D, and here we will get derivative of q by x 1 plus y squared minus derivative of p by y minus 1 plus x squared dx dy, totaling x squared plus y squared dx dy. Because we have circle, we have to switch to polar coordinates. We'll get rho square as x square plus y square multiplied by absolute value of Jacobian. We'll get rho cube d phi d rho. Here phi is changing from minus pi to pi, full circle. Rho is changing from 0 to r, from inside of circle, from center to outside, r. Rho cube d rho. We'll get 2 pi multiplied by r power 4 over 4, and which will get us pi r power 4 over 2. However, we cannot always apply this formula. Let us have same contour. And here we have integral by L x dy minus y dx divided by x squared plus y squared. And the problem is that we have p equals minus y over x squared plus y squared, q as x over x squared plus y squared, but they are not continuous inside this circle. At point 0, 0 we have division by 0 here, division by 0 here. So Green's formula is a no-go. We will do it manually without this formula. So to do it, we have to parameterize this curve. We have to write down parametric representations of this circle. This will be r cosinus t and r sinus t. Now we change here everything to t will get integral from 0 to 2 pi, and here we get r square cosinus square t plus r square sinus square t. In the denominator, r square sinus square t plus r square sinus square t dt. And we see that these two expressions are actually the same, so we just get integral from 0 to 2 pi dt, which is 2 pi. We cannot calculate this expression using Green's formula, but we can do it in the old-fashioned way. Next example. If we have integral from 0, 0 to 1, 1, and we have x squared minus y squared dx minus 2xy dy. If this expression under the integral, if this expression is full differential of some function, then we are free to use any curve that connects 0, 0 and 1, 1. Let's check it. So we have b equals x squared minus y squared. Q is minus 2xy. So to be full differential, dp by dy has to be equal dq by dx. But d by dy of x squared minus y squared is minus 2y. d by dx of minus 2xy is minus 2y. They are equal, so they are full differential, and so we can calculate this integral using the simplest line we can find to connect 0, 0 and 1, 1, line y equals x. So this integral will be transformed to integral from 0 to 1. X tends from 0 to 1. And if y equals x, then we replace everywhere y with x. So we'll get x square minus x square minus 2x square dx. And we get minus 2 integral from 0 to 1 x squared dx, which will be minus 2 over 3. Let us continue this example and find out what function can be represented as x squared minus y squared dx minus 2xy dy. What function u has to be. We will do this using the formula u equals integral from x0 to x p of t y0 dt plus integral from y0 to y q of x t dt plus constant. At point 0, 0 this function is continuous, p and q, so we can just integrate from 0 to x. Integral from 0 to x, p of t0 will be t square dt plus integral from 0 to y, q of xt will be minus 2xt dt. Now, integrating first one, we get t cube over 3 from 0 to x. Integrating second part, we will get minus 2x by t square over 2 from 0 to y. And we will get x cube minus 2xy square. X cube over 3. Now we have restored function u of x, y, which served as an origin for this integral.